Hi everyone, welcome. I wish you a very warm welcome. Today's seminar is a joint seminar with CEME and CAE. The title is Bioinspired Antifreeze Design of Cellulose Gels for a Circular Economy. Dr. Aakash Kumar from Stony Brook University is our speaker. Dr. Kumar is a research scientist in the Department of Material Science and Chemical Engineering at Stony Brook University. He received his BTech in Metallurgical and Materials Engineering from National Institute of Technology, Trichy in India. His PhD was from Material Science and Engineering from the University of Florida, where he worked with Professor Susan B. Sinott. Then he worked as a postdoctoral associate at UPenn with Professor David Strolowitz and at Yale University with Professor Diana Chu. Dr. Kumar's research interests include computational and theoretical modeling and framework development of bio-inspired materials, as well as understanding and designing material interfaces with applications in energy and power electronics. So thank you so much, Dr. Kumar, for doing this, and it's all yours.
Thank you so much, Professor Suraneni, for this wonderful introduction and this kind opportunity to present my research today in this seminar. I'm also grateful to Professor Solo Gabriel. I don't know if she's joining us, but yeah, for the invitation. So I'll just share my screen first and then start my presentation. So I hope you can see my presentation now in the full screen mode.
It's perfect.
Awesome. Thank you so much. And so thank you again for talking about the title of my presentation. So today, most of the presentation that I'll be covering was just recently published, and I give the reference here. As Pranay mentioned, that I mostly focus on materials modeling, and interfaces is a key aspect of my research. And because this is such a nice, diverse audience that we have from different departments, including civil as well as materials and chemical, I thought it was good to just focus on these two sort of big terms that I have in my presentation, which is circular economy as well as bioinspiration. So, I mean, I don't think it needs to be introduced to this audience. A lot of you must be working on, how to make sustainable materials as well as environmental friendly materials in line with circular economy. But just to give you sort of a background, linear economy is what we have known for quite some time, where we really design something and then use it and then we throw it away. And we have had this huge focus on recycling in like maybe last few decades or so, where we have tried to do recycling of materials. But one thing we have to admit is that when we recycle a lot of the products, they lose, I'm sorry, their value. And if you have followed the news lately, that a lot of the nations where, for example, US and many other countries used to ship off their plastic waste, for example, they have stopped importing a lot of those waste. So that means we are stuck with this huge issue that, we may be making things cheaper and we may have a lot of possibilities for recycling, but now we don't really have anywhere to dispose them. And so this brings us to this very important, powerful idea about the circular economy, where I think the main focus is to keep products and materials in circulation for as long as possible, right? We could use things like recycling, repairing, and just repurposing in such a way that the materials remain in circulation. And recently, there was a very nice theme on Nature Reviews materials, where there was a lot of there were like very good papers where they were all mentioning how we can focus on materials design when we are talking about circular economy. And then I think since we are always focused on targeting properties and functionality, I think we also have to take into consideration some of the other major issues surrounding us. So more relevant to my research, climate resilience becomes very important. And I know a lot of you working in Miami also have this as a core focus and theme of your research. So this is an article from almost like a week ago, even less than a week ago. And I mean, maybe you must have been following this in the news, that there's a lot of land subsidence that's going on in the Arctic regions, such as Alaska. And so there's a huge, huge threat to the communities living there, because the infrequent water ice freeze thaw cycles, they lead to these cracks and infrastructure damage, as well as loss of wildlife and human life in these regions, right? And so that's where my project has sort of revolved around in the last 1.5 to 2 years. And the focus has been this freeze thaw damage that we see not only in the Arctic regions such as Alaska, but also even in like Northeast US, I would say, where you have like damage to buildings, damage to roads. How could you improve those properties, right? And so if you're thinking of concrete, which is again a common, a big focus for many researchers, like how could you increase the damage resistance, the freeze thaw in particular damage resistance of concrete? And so before I get into more details, again, as I mentioned, the bioinspiration part, when I was a graduate student at Florida, in my department, we had Professor Anthony Brennan. I think he's an emeritus professor now. And they had developed something called Sharklet, which would inhibit bacterial growth. And I do believe they have this company, so that was my first sort of introduction to what is bioinspiration. And so in their work, they were focusing on mimicking the skin of sharks, which are naturally they have this anti-fouling, antibacterial properties, and so they use this artificial skin for medical purposes such as catheters, as well as just using it in like even in like regular clothing, right? And so in my work, we also draw inspiration from nature, and there's a good number of examples that you can see when you have fish and bacteria as well as insects that can survive extreme cold, right? So temperatures are well below zero, but they're able to survive. And how do they do that? So this is an image of an insect, a spruce budworm. So what they do is they produce something called an antifreeze protein. And let me just make sure I have my pointer here. Okay. So what they do is they produce something called an antifreeze protein, which has the capacity to identify different ice planes and go and bind to those ice planes, at the atomic scale, and then that leads to the ice retardation. The growth doesn't happen, right? And so when you think about sustainable materials, right, first, one of the few candidates that you will always think of is cellulose, and that's where we also wanted to sort of look to begin with. So cellulose is the most abundant biopolymer on Earth. It's a great material because we can avoid having toxicity and worry about recycling and like the waste disposal because it's a natural material that can again go back and decompose on its own on the ground, right? So if you look at the different crystallography of cellulose, cellulose has this sort of sugar chains, these chains that are connected that lead to sheets, and then they are stacked in this AB format, which give rise to these crystalline structures. So cellulose has this 1-beta structure here. And then cellulose occurs in different forms. But interesting thing to note for this talk, especially, is that they have, if you focus on a chain of cellulose, they have these glycosidic bonds, right? So it's the same bonds that you see in sugar. It is in fact these sugar chains for cellulose, right? And so again, related to this work, we collaborate with Professor Ben Shao at Stony Brook, and they have a novel way of processing cellulose. So this is called a nitrooxidation process, which is less energy intensive, and they can produce these CNFs, cellulose nanofibers at scale using this method, right? So this is just showing you the setup, how they treat it with nitric acid, and then how do you get these very high quality CNFs, right? So interestingly, what they were after was trying to use CNF solutions instead of water when you're looking at cement. And so what they did was they used this to test out how does the cement behavior works. And again, this is a very recent paper from their collaboration with some other experimental colleagues where they tried different compositions of these cellulose nanofibers in cement. And then they looked at different kinds of properties. And especially when they focused on the freeze thaw resistance, they noticed that you had like less decrease of dynamic modulus as well as less decrease in mass loss for the cases where you had CNF instead of the control cement, which just had water, right? And so they also did other measurements and concluded that chloride ingress, which is again an issue with a lot of the concrete failures, that was also lower in many cases compared to the water, just the control cement, right? So that's where we also want to come in. And like modeling of cellulose and water, for example, is essential if we want to understand what happens at the atomic scale, and like how can we further optimize and develop these kind of gels um, for different types of properties, such as an antifreeze material, right? And so, as we already know, that these cyclical freeze-thaw processes, right, in water and ice, they account for major infrastructure damage, right? We are very familiar with these kind of sites around us in the extreme winter, right? And this will only increase because of the rising temperatures. We have these global rise in global warming, as well as it's especially going to impact, these Arctic regions, like the image I had shown of Alaska, because they have this something called permafrost that is basically degrading, which leads to this infrastructure damage, right? And so that's where, if I really like this image of materials modeling, because you see how we can really go from the very, very tiny scale where we're looking at individual electrons, and we are modeling these atoms for their fundamental interactions, and like able to build on top of these huge phenomenological models, or even more physics-based models that can really predict the behavior for example, a cement performance, or large-scale engineering behavior performance could be predicted at the macro scale. And we should be able to take into account these fundamental interactions at the smaller scale to account for that, right? And so that's basically my focus, which is we need to account for these fundamental interactions at different scales. And so this multi-scale approach is essential here. And in that sort of umbrella of multi-scale modeling, my research falls mostly in the really bottom left, which is to include the electronic effects, which is the ab initio, so-called ab initio method. That's where they come in, as well as building on top of it to look into more classical mechanics at these atomistic scales. And so with that, I think it'll be this will be like a one slide introduction of what density functional theory is. So some of you might be aware of this really powerful tool that can compute very accurate energies and forces. And so basically, it is a way that we solve Schrodinger equation by recasting that problem into something known as Kohn-Sham equations, right? So the main major challenge about Schrodinger equation is that it has a many-body problem, right? And how do people get away with that? Well, it was through some work in the 60s and 70s, Kohn and Sham had worked out certain equations, right, where you can basically recast the problem, the many-body problem, into a single particle wave function if you assume that all the electrons, we are trying to solve for, they do not interact, right? So I'm not going to go into too much detail. I did teach a class recently also. If there is a link I posted, it's a very mini course for DFT, which also includes how do you do these calculations. So for this seminar, I don't think it will be a good idea to go into too many details of this, right? That will be like another talk. But I do have this nice plot here that shows how number of publications that utilize DFT or focus on DFT have exploded exponentially, right? So it's one of the most popular tools, I would say, in materials modeling, and it has been associated with 2 Nobel Prizes also in the last 3 decades or so. So coming back to our major focus on antifreeze materials, right? So we know that antifreeze materials, or these proteins, they have this ability to arrest ice formation, right? They could inhibit ice nucleation to begin with, or they could do this binding to certain ice planes. And for that, we have another very good example. This is like a computational setup, but it shows how this insect, again, it's an insect called Tenebrio molitor. They have this antifreeze protein that goes and identifies ice planes and attaches by forming this sort of a clathrate type of motif between their ice binding plane, which is on the protein, to the ice, and that sort of retards the ice formation, and they are able to survive extreme cold, right? In fact, antifreeze proteins have been looked into quite some detail throughout, for many, many years. And one of the reasons is because they are only found in these small insects and bacteria, right? So there's always an interest in being able to artificially make these kind of proteins because of their, amazing applications. If you think about cryoprotection for medication, even food storage, right? So they could be classified into different types depending on which planes they bind to, right? So this is a good reference for that. One interesting thing that you will notice is that a lot of these antifreeze materials, they have a sugar backbone. So similar to what I had, shown for cellulose, right? And so that's why cellulose does become like a very interesting candidate to explore its behavior in antifreeze, in the area of antifreeze behavior, because it also has these glucose chains. And this is where DFT, the model I just introduced, is amazing at, because it can really account for the fundamental interactions. So to begin with, if we just focus on a cellulose crystal structure, which is this 1 beta, and then compute the basic, very relevant properties to come up to understand basically how the crystal structure looks like. So we can see that the calculations that we carried out using these details, which I have here, they match really well with the experimental values for example, lattice parameters, as well as these glycosidic torsional angles that they have. So these are also very important to describe the mechanical behavior of cellulose. And so these are the results. And they actually have this correction inbuilt into the calculations, which is called a D3 correction. That is important because, as you know, that this material has a lot of hydrogen bonding and van der Waals effect, and so you want to include this in your models. And so with this, I present to you the basic characterization of cellulose using DFT. And so if you were to label different carbon and oxygen atoms, and this is the convention that's been used to do that. Now, getting into ice. Ice is another very interesting material for everyone, and especially is surprising and also like a mysterious to an extent, because there are so many different phases of ice. So every now and then you always have a new phase that is explored and that is discovered. But for the most part, hexagonal ice remains the most widely used structure. And so in our present work, we also focus on hexagonal ice, which is given by this one hexagonal. And so for our model, we choose this 48 atom cell. It's an orthorhombic cell that is from the work of Morrison. And the nice part about this cell is that if you have an orthorhombic cell such as this one, you can just basically focus on each of the XYZ directions, and they correspond to either the basal planes or the primary prismatic or the secondary prismatic planes. And so this is something we wanted to explore as we were interested in looking at cellulose binding and all of these different planes, right? So again, going back to the cellulose model, cellulose is a huge polymer, and it's very difficult to really explicitly model all of the complexity that comes with having the entanglement as well as the large structure of cellulose. But one thing that is very relevant here is that when you have cellulose breaking down, it actually involves breaking of these glycosidic bond that I just showed, where you have, if you label them as C1 and C4, that's where the breakdown happens, right? And so this is there's a lot of mechanisms that have been proposed, but usually they all center around breaking either this bond or that bond. So it's a C1 C4 cleavage, right? And because nitrooxidation process that we are following in our work is also, it also involves treating cellulose with nitrification as well as oxidation. I think we also wanted to go with that and also help us sort of narrow down our choice for the model. So what we have is this reactive unit of cellulose, and we call it reactive because to make this model, we have to take a chain of cellulose and then break this C1 and C4 bond, because in that way we are mimicking what happens when you have the cellulose being treated, and then it's binding to ice and water. And so with that, we can proceed. Once we have the choices made, we can now compute the binding energy, right? This is where, again, DFT is very powerful because we can get really good energies and idea about like how does cellulose like to bind to ice. So if you have this heterostructure of cellulose on top of ice, which I refer to as EI hetero, I being a position sort of reference, then we can say that this energy is equal to the energy of ice as well as cellulose plus the binding that happens at this particular position. And for a different configuration, for a different translation of cellulose, we can also similarly have another equation that connects these properties at that particular position. And so this is how we can span different positions just to get an idea about the energy landscape when cellulose is attaching to ice. And the nice thing about this equation is that if you take the difference, then basically the terms that involve the calculation of energy of ice and cellulose, they cancel out. So in a way, the total energy changes that we get from our DFT calculations, they also reflect the relative binding energies that we have for cellulose at this different size. And this is actually a very central tool or theme about DFT in general, that we don't really focus always on the number or the energy that comes out of the calculations. But if you take it in a relative way, then DFT is very good at giving us a measure of the stability as well as the relative strength in our case, like where cellulose is more, preferential in binding. So once we have that expression set up, we also want to include many different types of variations. And the basal surface of ice has also received a lot of attention in literature. So the most stable surface is known as the Fletcher surface. And it's a striped surface where you have these alternating rows of oxygen and hydrogen. And so that is known to be the most stable until you get to about 32 Kelvin, when the disorder sort of takes over, and then you lose that sort of really nice sort of this alternating row pattern. And in our model, if we were to just cleave the surface or cleave the planes to create a basal surface, we would have what I call here as pristine surface, which means you would be breaking some of those hydrogen bonds on top of oxygen. And so that would leave some oxygen atoms sort of really, short of their valence, right? And then we also considered another case where we saturated all of those missing hydrogen bonds manually. And so we call this a fully hydroxylated surface, where you don't have any surface oxygen that lacks a hydrogen bond, just to get an idea of how is the proton configuration of the surface hydrogen configuration also connected to the stability of cellulose binding to ice. And so these are the structures before the energy minimization. And then we also consider different translations, as I had shown in the formulation of our setup. So totally, we had 15 cases for each of these three different surfaces for the basal plane, right? And so we are able to obtain these energy maps or the contour maps for these binding energies. And the darker regions basically reflect the most preferred binding configurations, or the energy or the configurations that had the lowest binding energy relative to the other cases. And so the supers or the annotations of numerals on these are actually reflecting these individual structures that we considered. And so they all are the most stable configurations, if we can call it, when you have cellulose binding to these different surfaces. So one of the fascinating things we found in some of the cases is that we have cellulose attaching to the oxygen atom of these ice surfaces and leading to this CO bond. So that was kind of interesting. And that pattern was actually very common in many of these, most of these actually, these low energy configurations. And the other thing we noticed was for the case of the hydroxylated surface, where you have all of the hydrogen atoms, like satisfied, we had this disintegration, or basically, they reject these surface atoms, which means they don't want to be. This is not like the most stable configuration. This is not what is preferred when you have cellulose on top of ice, right? And so we can just plot all of this energy sort of landscape that we have. And so we do know that the larger binding energy that was observed for the hydroxylated case was actually the case where you had the surface disintegration. So those are not actually stable surfaces, even though the plot suggests that, so that's actually a minimization because they don't want those hydrogen atoms to be there, right? And this is the region which is the actual stable surface, the structures where you have cellulose binding to ice. And all of them, which are shown here as 1 to 6, right? We focus on them because these are the most stable configurations. And so one thing that we noticed when we really dive deeper into these structures is that they all have the formation of this CO bond, which I just mentioned, right? So that's very interesting that after of all of these 30 cases, we have these 6 structures where we have, the CO bond formation, right? And so if we focus on like few of them and go deeper, what we noticed was that there is a tetrahedral geometry being observed. So the angles that carbon forms around this sort of group of atoms, they are near tetrahedron. And so that warranted like further sort of investigation, right? And so I'm just showing you a side view of one of those structures that before the optimization, before the energy minimization, you have cellulose sitting right here, and then you can see how these colored atoms, they sort of change their orientation. There's almost like an umbrella crowding effect that leads to this tetrahedral geometry. And so that's where we were really excited that we do have some common connection now where we can explain the cellulose binding to ice, right? But how do we quantify this sort of behavior? And so for folks who study water, there's a lot of different descriptors people use, and there's one called the degree of tetrahedrality, which is a measure of how perfect of a tetrahedra a certain geometry is. And it just measures basically the angles that surround the central atom, and then you can compute this using this expression, which was sort of originally proposed by Chow and Hardwick in the 90s, and then it was refined and normalized by Errington and De Benedetti. And if the value is close to 1, then you have something called a perfect tetrahedra. Whereas if it's close to 0, then that's more like an ideal gas, right? So in our case, we do sort of observe like a really nice tetrahedra. And so we set out to compute these Q values. And we found for all of the 6 cases that I just shown, they are very close to 1. And so that's where we were really sort of looking forward to what happens. Why is this an important aspect of the cellulose binding? And so we do believe that that means that cellulose prefers a tetrahedral geometry with ice surface, which is not surprising if you think about it, because ice and water also have a tetrahedral geometry. So it is natural that they prefer forming a tetrahedral geometry with a closely compatible system if it is not ice and water, on its own. And so this is what we also published in this work that I had mentioned. And after doing that analysis for the basal planes, we also wanted to study prismatic planes, as we do have a lot of literature that suggests that a lot of these antifreeze proteins, they bind to prismatic planes. And so we considered both the primary and the secondary prismatic planes. So these are shown here, and then we repeated our analysis with these contour maps for the binding energy, relative binding energies. And then here again, I label the most stable configurations. And so this is sort of the test case, or sort of the schematic where we have cellulose sort of sliding on for different translations on the primary and the secondary prismatic planes. One interesting thing we noticed was that here also we do have that CO bond forming, which you can see here. And I don't know if it's very clear here, but yeah, it's this one here, if you can focus on the same CO bond that forms. But we also observe that there is a rejection of one water molecule, which means that the mechanism might slightly be different when you have cellulose binding to the prismatic planes. But the central theme again was that the Q values that we computed, they were very close to 1, which suggests that cellulose is preferring again to form the tetrahedral geometry with these prismatic planes as it was doing for the basal planes, right? So what does this tell us, right? Tetrahedrality is an intrinsic property of water and ice. So it's a very essential thing. And so we also wanted to see, okay, let's just assume we have a water layer on top of the ice surface, right? And we can optimize it just to see how they like to reorient. So if we were to start out with a random configuration of different number of water molecules, so we tried like 4, 6, and 8 different molecules, and you can see they line up really well, very close to 1, because this scale is only from 0.9 to 1, which means they're also very, very close to 1. So it's very evident that water and ice, they prefer a tetrahedral geometry, and cellulose has the capability to create this tetrahedral pattern on top of the ice. And so because these values are close to 1, that's what we have so far concluded. And so now I'm going to switch gears a little bit, because that was a very interesting sort of very deeper dive from DFT calculations. But those calculations, if I can just highlight the sort of the top view of the cell, they comprised of about 500 atoms or so. And because of the very accurate settings that we have to use for these DFT calculations, they took anywhere from almost a day to more than a few days, which means it's very expensive to really focus on these calculations if you're trying to come up with, like a bigger picture of how we can use cellulose for antifreeze. And so that's why we have to resort to something called coarse graining. And if you remember the first plot that I had where we talked about multi-scale modeling, right above electronic, we had something called an atomistic, and like above that is something called coarse graining, which means we can now group a certain number of atoms together to reduce the details in our model, but also make it simpler, but then also be able to access like a really large region of or the configuration space, as well as larger length scales, if I can say that, right? It will be almost like in the micrometer, hundreds of nanometers to micrometers, if we can use some of these powerful supercomputers. And so for cellulose, if we look closely, then there are these interesting sort of atom connections, I can call it, that repeat in our motif that we had used for the reactive unit. And so I label them as A, B, and so they are the same, and C. So they are the same. And so if we use this format, then we can represent the cellulose unit in something like this, where we have essentially compressed 42 atoms into 6 particles. And of course, they're nowhere like a real reflection because of the chemistry involved with different species. But if we were to just come up with a particle description of cellulose, then we would be able to use this model, right? And so in this case, the BC would represent the glycosidic bond. And so when you have this very heavy decorated atom structure, then that could become something like this, right? So you have basically lost the resolution, but you have increased the capacity to model more particles, right? And so for this one, we also have water here. So you'll notice that the water has lost the hydrogen atoms, and they are actually modeled at the MW level, which is a very useful tool, very useful potential, if I can call it, when people trying to model water. It was developed by Molinaro's group at University of Utah, and it's still very widely popular for modeling water behavior. So we use that for water, right? So I would, because of the time constraint, I don't want to get into the details when we have a complex cellulose model here, but I just want to explain or give a very sort of a quick overview of what a model like that could be used for, right? And so we can have a simpler case. So forget about the 42 atom to 6 atom transformation that I just showed. If you just have a gel or like an antifreeze, potential antifreeze material that we're talking about as beads of monomers, right? As I've shown here, and this is the work of Shaumik and Dilip in our group, then we can also use this to study like a model system if you were to use this for an antifreeze property, right? So here, these beads, these monomers, they are represented by this bonded interaction, which is basically like a spring term for the energies. And then water again is at the MW level. And then we can consider the interaction between these gels and the water molecules using a Lennard-Jones potential. And because we know that cellulose and ice and water, they like to bind very well, we can use a hydrophilic sigma, which basically suggests that they will bind really well. So we can play around with sigma values such that we do see that hydrophilic behavior, right? So that's the simplicity and advantage of using a Lennard-Jones potential, right? So this gel can then go into something like a massive water system, right? So we have these this H2O explicitly being reduced to like one particle, as I just mentioned, using the MW model, right? And so we can then use something called molecular dynamics simulation, right? We use LAMMPS package, and we can now have this ensemble in the NPT ensemble. We can have almost 10,000 particles, which is really like a much larger axis of the length scale compared to what we had at the electronic level. And so once we do that, what we are interested essentially is simulating the freezing of water in the presence of these gels. So we can go from 300 Kelvin to 180 Kelvin, right? So the way the procedure is set up for our case is we use a cooling rate of 1 Kelvin per nanosecond initially, and then from 220 to 180 Kelvin, we actually make it even slower. And this whole simulation runs for about 500 nanoseconds. So what do you get finally? So you have this water And then once we freeze it, we have different types of ice phases. So these ice phases are recognizable by their crystallography. So hexagonal ice is what I was modeling. You also get a lot of cubic ice, interfacial ice, as well as some of the hydrates that form. This just because we are trying to mimic an actual formation of ice when you go from water to when it's cooled in a super cooled state, right? We don't have like a wall that can do like a heterogeneous nucleation. So it's very difficult to sort of simulate homogeneous nucleation. And so that's why this is what we get, which is also seen in the literature when we try to simulate something like this. Now, one thing what was very interesting for us was that water inside the gels that I had shown earlier, that did not freeze. So that's like a really powerful indicator that having a hydrophilic interaction like what we showed for the gels, it allows us to sort of have this antifreeze behavior, right? And so again, we wanted to test out, right, what does the tetrahedrality tell us? Because we do know that it's a very essential parameter when it comes to not just describing water and ice, but also how the gel or cellulose, for example, in our case, might modify their orientation, right? So we again applied the same to all the particles, and then we came up with a representation in a statistical manner. And so what we see is that the Q is value is about zero 0.8 when you consider liquid water, and it's very, very sharply 1. And again, this is something that's known in the literature already. So we do believe that this is a good sort of an agreement that we do observe, right? Like you have a Q value that changes from a lower tetrahedrality to a higher tetrahedrality, because we do know that ice is nearly perfectly tetrahedral, right? Instead of water, which is, there is the tetrahedrality, but this is also like there's a randomness involved. And so that was nice to see that our simulations do follow that trajectory. But what about the unfrozen water? So the unfrozen water that we have within the gels, which is shown here now, they are basically super cooled water. We saw that they have a tetrahedrality which is close to ice than being close to water. And so that's where we really have this idea that to design an antifreeze, we want to be able to tune the tetrahedrality, which is closer to ice but not quite ice, but it's different than water, right? So that's sort of the major takeaway that we see from these these large scale simulations. And then that's where the sort of the design of these antifreeze lies about the tetrahedrality. Now, one thing to notice is that, and this is something we are also exploring and expanding on, is that when we think of water, then we don't really have this perfect tetrahedral surrounding where we only have like a 4 neighbor for each of the central molecules, like you would observe for a perfect tetrahedra, right, in methane. So we can actually generalize the tetrahedrality parameter for a different n neighbors and then recompute, because we already see that for the case of water, which is shown on the left, we have more of under coordination. So, right, so there's more neighbors that have 3 neighbors rather than the 4 perfect neighbors. Whereas in ice, yes, it's more close to a perfect tetrahedra, right? So what we are observing is that we have these subtle changes in tetrahedrality whenever we introduce a solute as well as a gel. I mentioned solute because we're also looking into the freezing effect when you have something like a salt, which has these hydration shells that are going to again change the tetrahedrality. So in a way, we can say that tetrahedrality might be a common measure of how we can tune the antifreeze or the freezing point depression in a lot of these solutions that have that we are interested in for water. Again, very interesting observation was also shown in literature that you can always come up with these biomolecules or these peptide chains, for example, here. They have these small hydrophobic groups that enhance the tetrahedrality, right? So for a tetrahedral system, we want the angles to be around 109 degrees. And for a lot of the biomolecules people looked at, they noticed that they have these small peptides which have these small hydrophobic groups that can enhance the tetrahedrality. And it's actually very similar to what we are seeing as well, because our cellulose is a really small, tiny molecule, or I guess the choice of the representation of cellulose that we had was really small. And they do have these really, tiny hydrophobic groups that attach and preferentially lead or enhance, if I can use that word, tetrahedral character. Uh, And so that could be direction to keep looking in when we're trying to design and even discover new materials that might have like an affinity for tetrahedrality and also an antifreeze sort of nature. So I think in the last, I think 40 minutes or so, I've really tried to focus on how an inorganic and organic interface can be used to design an antifreeze material. But I thought in the last like 10 minutes or so, maybe 15 minutes, I would try to also give a glimpse of some of the other work that I have done. And so my research has focused on material interfaces, which is also within the same climate energy sort of umbrella. And so one of the first works I did in this area was as concerning metal ceramic interfaces. So metal ceramic interfaces are basically ubiquitous. You will see them in everything. So if you have a perfect lithium all solid state battery, then you have this lithium anode in contact with a ceramic electrolyte, right? You have a superalloy coating. They also have these metal ceramic interfaces. And of course, in microelectronics, we have these MOSFET devices where you have the silicon, silica, sorry, metal gate and silica or hafnia sort of interface. So it's of course like it's easy to really picture that the integrity of this interface is very critical to performance of these devices. And so we wanted to ask a question that because you have like such a large area or like a path at the interface, right? If you think of diffusion across lattice, across dislocations, grain boundaries, and we do know these are high diffusivity paths or short circuit diffusion paths, then we wanted to ask where does the interface diffusivity between a metal and ceramic would fall into this sort of scheme. And so we had some experimental observations that supported or sort of led us to our findings. And in those experiments, they basically had put nickel on top of sapphire and then annealed the system for about 10 minutes. And so what they noticed were these through thickness holes began to form, and you would have a lot of nickel being deposited around the rims. That was kind of a puzzling effect because the volume, if you looked at the rims that was deposited, that was only half of the volume that was lost. So you basically have a lot of material going inside, but only half of that being accounted for, if you think of the rims. And so one big giveaway though was that the thickness of the film began to, increase. So we strongly suspected that maybe what is going on is that nickel, when you have this annealing, that they go down these grain boundaries and that they redistribute along the metal ceramic interface. That means that the diffusion could be really high here, which means you see this thickness increase, right? So again, just to highlight how DFT is so powerful in looking into these really fundamental interactions, right? So we started with this model where I'm showing you nickel on top of sapphire. And so we started calculating the vacancy formation energies, right? So we looked at different defects as well, but here I'm going to just show you the major sort of finding, which suggested that if you're close to the interface, which is this measure here, the distance d, for different types of sapphire terminations, what we observed was that the vacancy formation energy really drops. And the only anomaly that we saw was a different special case where you had like an ionic bond forming between nickel and oxygen. So this was an outlier. But overall, the vacancy formation energies really dropped from these DFT calculations, which suggested that you have a huge dominance of these vacancies. So maybe they are the vehicles of this very fast transport, as we were trying to speculate earlier. We also wanted to study, like how does the migration of these vacancies would be along the interface, right? So this is, we call it a nudged elastic band. It's again something you can do with a DFT calculation. So we're able to compute this migration path and the barriers associated with this path. And so they happen to be like almost half of what you would have for like a diffusion or like a migration within perfect nickel lattice. So both the fact that the formation energy was really low as well as the migration energy being low was a very strong indicator that diffusion is really fast at these interfaces, but it is not universal as we were trying to establish that. And so what we did was we came up with a descriptor, which is basically this ratio of the formation energy of the vacancy at the interface compared to the formation energy of the vacancy in the bulk metal. If you take this ratio, this would match an experimentally observed quantity, which is the work of adhesion between the metal and ceramic, as well, and given that ratio with the surface energy of metal. So that was interesting because we found this from some experimental literature, and we were able to tabulate this for all possible cases. And we did additional DFT calculations, and we saw that they pretty much follow the trend. So that was kind of a very interesting finding. And so this became like our diffusion descriptor for interface. So that's something we worked on. So sticking to electronics, again, just to give you another glimpse of what currently I'm involved in, silicon carbide is another very popular material that's being looked at for electronic application. And because it has a higher band gap than silicon, it could be used for more energy intensive, like high voltage, high power consumption, sort of where you have requirements like that in those sort of situations. And so again, we can use DFT to compute basic properties. But one key issue when you have silicon carbide is that you have a lot of defects. There are these planar defects known as dislocations. And so this is something we have been investigating with Mike Dudley's group, who really are very experts at growing these silicon carbide films. And so what they have figured out is that the growth of silicon carbide is via a step growth. So it's always going to be a step growth. So they have, these steps. They, instead of having like a flat surface to grow these systems, so they use something called a step. And so I did some calculations which showed that if you do have a step, right, compared to like a sharp step. So I have this model that have the exact same number of atoms, but if you focus on this particular aspect of the structure, that you'll see that there is a smoother step compared to this sharp step. But we find that having steps actually makes the surface and the structure more stable. So currently we're investigating the stability of steps, because from experiments, they can have an idea that, when you have these steps, you can grow it. But, the powerful aspect of the modeling work is that we can really come up with commit, like a best optimized surface, if I can say that, and then maybe use that, for the experimental colleagues to try to deposit and grow this. And so that's something we are very, interested in. And then finally, I also wanted to just, again, emphasize, how interfaces are so relevant. So this is just the image of the interfaces that I had presented earlier. And, I also did some work with batteries. So we have 2D materials. I mean, it's very popular these days. A lot of people use 2D materials for different types of applications, but they're also very relevant for battery applications because they have these van der Waals gap, right? So if you think of a traditional cathode, such as a lithium iron phosphate, they have stoichiometries in dictating how much lithium you can really pack in. So it's as simple as that. Whereas when you have something like a 2D material, what you have are these amazing endless spaces, these gaps where you can store lithium, which improves the capacity, the theoretical capacity for the batteries enormously. So we were interested in this behavior for MOS2, which is a semiconducting phase. But as soon as you add lithium, it leads to a phase change to form like a metallic phase, which is called in the 1T phase. So we wanted to see how does this behavior change if you start using something called a substrate, right? So we tried two different materials, which is hexagonal boron nitride and graphene. So what we noticed was that if you have hexagonal boron nitride, then the lithium intercalation basically remains the same. There's no change at all, as if there was no substrate. But in the case of graphene, right, we noticed that the phase change did not occur, at the same pace, and you had to put more lithium, keep putting more lithium to enable that phase change. And this is again, the experimentalists were really interested to know what is going on, and DFT gives us like a really good picture of what could have happened there. And so we were able to compute the charge density. So this is what I'm showing for boron nitride as well as for graphene, and you can see that the graphene case, the charge density is lying more on graphene, which means it takes up the charge that lithium had that would have been earlier donated to MOS2 to lead to this 2H to 1T phase change. Whereas in the case of boron nitride, it's a very well behaved. It doesn't really take up those charge, and so it's available to lithium, so it can lead to that phase change. And so that's what is highlighted here. So it also opens up a new avenue when you have something called a substrate engineering, right? You can have different materials stacked together. And this is essentially where 2D materials shine, because you can really stack them in different ways and come up with interesting properties. But yeah, our work suggested that we can if you have graphene, then that would reduce the doping power of lithium by almost 60%, compared to hexagonal boron nitride. So yeah, these were just some of the slides I just wanted to also present, but I think I'll quickly come back to the summary of my major sort of portion of the talk, that cellulose is a very important candidate for a lot of the bioinspiration and also sustainability efforts that could also fit in really well with the circular economy goals. And in our findings, we saw that the cellulose has this really strong preference to ice planes by forming this tetrahedral geometry that involves the carbon atom from cellulose and the oxygen from the ice planes. And then cellulose prefers this tetrahedrality, and we can compute this using the degree of tetrahedrality. In most of our cases, we saw that this value was 1. And then our coarse grain model also suggests that the gels are essentially doing the same thing by modifying the tetrahedral characteristics when you have a clear distinction between water to ice, but the gels can modify that in such a way that you could have unfrozen water within the gels, for example, in the case I showed. So most of the work that I talked today is available. It was just published recently. If that might be of interest to you, and I will thank the computing that we have from IACS, which is where the supercomputers are housed, and funding from Stony Brook for this research, and acknowledge a lot of the members in this team. So Dilip Ben Shao is the experimental colleague who worked on the cellulose nanofibers that we are interested in exploring. And TJ Kim is leading the efforts with solutes. So you have these salt solutions that also, have this freezing point depression. And we're trying to see if we can have this common expression, whether you use gels, whether you use solutes, you can define, the antifreeze behavior, and then the postdocs associated as well as the graduate students associated. So yeah, I think with that, I'll just end my talk, and I'll be very happy to take any questions. Thank you so much again for listening and your patience for 50 minutes. Thank you so much.